Hello Year 12, how you doing? I hope you're well, looking after yourself. Right, so we're going to move on from what we did last week on resistivity and we're going to go back into doing some circuits. Now this is where your skills are really going to start to show. Just before Easter I asked you to look at resistors in series in parallel. Hope you've done that because we're going to need that skill really going forward. What we're going to look at today is energy and power and these equations here. And we might just have a little look at EMF in cells in series and parallel. Right then, so energy and power then. So power in electricity, or electrical power if you will. Right, so electrical power. What does power mean? Well, you should know from GCSE or perhaps even from mechanics that power is energy over time. So power is measured in watts, and what we're saying is 1 watt is equal to 1 joule per second, right? So if I have an electrical appliance, for example a toaster that's maybe 1000 watts, we're saying that 1000 joules are transferred every second, and that gives us our power rating for the appliances. Now everything that transfers energy has a power rating, so that even the humble resistor has a power that's going through it. That's energy that's going through it. It's transferred into heat a little bit, and it therefore has a power rating. The bulb would have a power rating. A heater obviously has a power rating, and the ones that transfer energy the most will have a higher power rating. So the heater might be 500 watts, whereas a normal resistor might be only 2 watts, and a light bulb 36 watts or whatever. Okay, right, so the 3 power equations that are very useful when we talk about A-level electricity. We start with our basic one here. P is equal to E over T. But in electricity, sometimes we need to know how much energy has been. So if we take the T up here, E equals PT. Right, brilliant. No, in fact, P equals E over T, right? So E equals QV. You don't know what that means. It's the energy required. What 1 volt is. 1 volt is 1 joule per coulomb, rearranged. So P equals E over T. E equals QV. Right. But then if we take the Q and the T here, what does Q over T equal? That equals I. I equals Q over T, or Q equals IT, or whatever. Which means we get our first one. So our first electrical power formula is P equals IV. Really useful one, that is. Okay. From Ohm's law then, V equals IR, we can then substitute that into. So we can take Ohm's law and basically we're going to substitute it in. First up we're going to look at I. What does I equal? I equals V over R. So if we substitute that in there, P equals V over R multiplied by V equals V squared over R. Okay, and then let's take the other one. What does R equal? R equals V over I, which means that P equals, what does V equal? V equals IR, so we get I times by IR equals I squared R, which leaves us with 3 formulas then. First one being PIV, second one being V squared over R, third one being P equals I squared R. And which one you use depends on the information you're given. So if we have a light bulb that's 12 volts and 36 watts, and I've seen this kind of thing come on, well, we can work out the resistance of that light bulb, can't we? P equals what we're given, V squared over R, which means that R would equal V squared over P, 12 squared over 36, and whatever that would be. Sorry, can't see that thing. There we go. Or if we have a resistor that is 50 ohms, and we've got power of, I don't know, 20 watts. What would be the current going through it? We'd use P squared, P equals I squared R, I equals P over R square root, and that would give us the current. Alright? So those three formulas are super useful. And the past paper questions that I'm going to be giving out today are, or well, for your work this week, are basically revolving around those and a little bit of other stuff that we've been doing in recent times. Now, it's very easy to forget these sometimes. They are on your data sheet, but when we're doing electrical circuit problems, which we'll be doing over the next couple of weeks, you really need to be making sure that you are on point in, like, being a detective, finding the clues and working out the puzzles. I'm just trying to get us to a point where we know all the key bits. Okay, so those are the power equations. It just basically means how much energy is transferred. This one sometimes is called a power heating equation, because it sometimes talks about how much heat is lost by going through a cable with the I squared, and so on and so forth. Okay, so that's the first part of today's video. Just want to go over the next part now. The next part is about cells in series and cells in parallel. Cells in series and parallel. Right, so the cells in series is quite easy. The EMF, so the EMF is the symbol epsilon, and it tells us the electromotive force. Right, the electromotive force is basically telling us how much force the electrons are being pushed by, and it's measured in volts. So if we've got 6 volts across here, the EMF is 6 volts. It's the energy that's delivered to the circuit. Right, now if we add cells in series, the EMFs basically add up. So which one is the positive end on here? It's the long one, right? If we say each cell is 1.5 volts of EMF, how much is going on here? Well, we've got 1.5 plus 1.5 plus 1.5 is 4.5 volts. Easy enough, right? No, there's no real difficulty in that. But if we turn one around, which why would you? But there we go. Right, so we've got 1.5 going this way, 1.5 going this way, but then 1.5 going that way. So these two would cancel each other out, which means you'd have only 1.5 volts. It's really important that they are facing all the same way, because the push will cancel out. Basically, if you have 2 cells like that, that's 0 volts. Pointless, waste of energy, waste of everyone's time. So that's cells in series. The EMFs just add up. In series, EMF just adds up. Simple. You should know that from GCSE, to be honest. There's no real big secret there. However, when they're in parallel, and I've seen questions like this which you'll have to do yourself, it came more in the like kind of A2 content of it. It came on a year 13 paper. It's a nasty one. I'll get it to you at some point. Okay? Then what is the EMF when we have them in parallel? Alright? Now for a reason I don't want to necessarily go into yet, because we haven't learned about internal resistance. If that's 1.5 volts there, well, that's 1.5 volts there, what would you reckon it would be? Well, there is a push from this cell going that way, and there is a cell from that push going from that way. So you're reasonably thinking that it would be 3 volts, like if it was in series, but it's not. Because they're in parallel, we treat them as two different circuits. So actually, the whole kind of EMF here, the total or the sum of the EMF here would be 1.5 volts. Okay, so you might say, oh, well, that doesn't really particularly make much sense, or why bother? Well, you do get more current. And that's what you get. You don't get more potential difference, you get more current. So you only get the same potential difference, but because something we haven't done, so each one of these will have internal resistance here, right, which we'll come to at a future lesson. But when we add resistors in parallel, does the resistance go up or the resistance come down? The resistance goes down, which means the current goes up, so you get more current basically coming through the network. But if we have, no matter how many we have, if we put them in parallel, which you'll rarely find, to be honest, it's a way of boosting the kind of current more than anything. If you put 3 volts cells in parallel, across here will still only be 3 volts. So it's just worth bearing in mind, because it does come up, and it's mostly cells would be in parallel, in series, sorry. So that, in that case, the internal resistance is add up too, which means the current will go down. But often we're told that the internal resistance is negligible, so we don't have to worry about it too much. Okay, right, so that's the key learning for this week. I want you to just recap. I'm trying to be faster this week because it took me ages to upload that video last week. So if any questions, please ask. Please be in touch. Alright. So 1 watt is 1 joule per second through an electrical appliance. We can use the whole E equals PT, but in more circuit kind of analysis we would use these 3 formulas. P equals IV, PIV, and we'll get from it what we can. So in this bulb here, what's the current, what's the operating current of this? If it's working at 12 volts and it's 36 divided by 12 would equal the current, which would be, that's 3 amps, isn't it? That's easy maths. So we know that that bulb needs to work at 3 amps, right? But if we could also work out the resistance of it by using this formula, and for this one over here, well, we could work out the current going through it. Or, and if we know the current, and we know it's 20 watts, so we can work out the voltage of PD across it, and so on and so forth. These 3 are really useful, easily forgotten about. This one's probably the most important. These 2 are probably the forgotten about ones that are useful when you need them, and of course they do test you too. And then cells in series, if you put them in series they add up, so if each cell is 1.5, if you've got 3 in series that would be 4.5, but they have to be facing it the same way. I mean, they'd only be trying to trick you out really. If you put them in parallel, you still only have 3 volts, but you have more current. Sorry, in this case you only have 3 volts. You only have what each cell is, and therefore get more current because the internal resistance makes it go down. Right. Okay, I'll leave you with that. Let me know how you're getting on. Okay, please, I need to hear from you. We've got to sort out the Teams thing. If you go on Teams, you should have had an email. I'll set up a meme competition just to make sure everyone tags in and knows how to use the software. It's pretty easy, it's pretty intuitive. Alright? Okay, look after yourselves. Miss you all. Bye bye.